Ladies and gentlemen, distinguished guests, thank you for gathering here today as we delve into the fascinating world of saline, a substance so simple yet profoundly important. Saline solutions, often overlooked in their simplicity, are a marvel of engineering and physics, playing a pivotal role in various fields, particularly medicine and industry. Today, I invite you to explore with me the intricate interplay of engineering principles and physical laws that govern the creation, utilization, and impact of saline solutions. At its core, saline is a solution of sodium chloride, NaCl, dissolved in water. The most common concentration used in medical applications is 0.9% W/V, weight/volume, closely mirroring the osmolarity of bodily fluids. This isotonic solution is fundamental in ensuring that cells neither swell nor shrink when exposed to saline, maintaining cellular integrity and function. This balance is crucial for patients receiving intravenous therapy, ensuring their cells remain stable and function properly. The choice of 0.9% saline is not arbitrary but rooted in extensive physiological and biochemical research. This concentration creates an osmotic pressure that is approximately equal to that of human blood and extracellular fluids, a condition known as isotonicity. Osmotic pressure is a colligative property, which depends on the number of dissolved particles in the solution rather than their specific type. In an isotonic solution, the movement of water into and out of cells occurs at equal rates, thereby preventing the cells from undergoing osmotic stress. This is vital for maintaining the homeostasis of patients undergoing fluid replacement therapy, as deviations from this balance can lead to severe cellular damage, either by lysis in hypotonic solutions or by conation in hypertonic environments. From an engineering perspective, the production of isotonic saline requires precise control over the concentration of NaCl. This involves the accurate measurement and mixing of solute and solvent to achieve the desired 0.9% W/V solution. Advanced instrumentation and automation technologies are often employed in pharmaceutical manufacturing facilities to ensure that the saline solution meets strict regulatory standards. This process includes the use of high-precision scales and volumetric equipment to guarantee the exact concentration, as well as rigorous quality control tests to confirm the isotonicity of each batch produced. The application of process engineering principles ensures not only the consistency and safety of the saline solution but also the scalability of production to meet global demand. The interaction of NaCl with water at the molecular level is also a fascinating study in physical chemistry. When NaCl dissolves, the ionic bonds between sodium and chloride ions are broken, and each ion becomes surrounded by water molecules. In a process known as hydration, the polar nature of water molecules, with their partial positive and negative charges, allows them to interact electrostatically with the Na+ and Cl ions. This dissolution process is governed by the thermodynamic principles of enthalpy and entropy. The enthalpy change, or heat of solution, is typically exothermic for NaCl, releasing energy as the ionic bonds are broken and hydration occurs. The increase in entropy, or disorder, as the solid NaCl lattice disintegrates into freely moving ions in solution, further drives the dissolution process according to the second law of thermodynamics. In medical applications, the precise administration of isotonic saline is crucial for patient care. Biomedical engineers have developed sophisticated infusion pumps that deliver saline at controlled rates to ensure that patients receive the correct volume and concentration. These devices often incorporate sensors and feedback mechanisms that monitor flow rates and patient conditions in real time, adjusting the infusion parameters as necessary to maintain optimal hydration and electrolyte balance. The engineering behind these pumps involves a deep understanding of fluid dynamics and control systems. For instance, the peristaltic pumps used in many infusion devices rely on a rotating mechanism that compresses a flexible tube, propelling the saline solution forward without direct contacts between the pump components and the fluid. This design minimizes contamination risks and ensures a steady, controlled flow of saline. The compatibility of saline with various medical devices and delivery systems also hinges on the principles of materials science and engineering. Saline must be stored and delivered using materials that are inert and biocompatible, preventing any chemical reactions that could introduce impurities or compromise the solution's integrity. Engineers select materials for saline containers and tubing, such as medical-grade plastics and silicone, based on their resistance to chemical degradation and their ability to maintain sterility. Advanced polymer science is often employed to create composite materials that combine strength, flexibility, and inertness, ensuring that saline can be safely stored and administered without adverse interactions. Furthermore, the role of saline in therapeutic applications extends beyond simple hydration. It is used as a vehicle for drug delivery, where medications are dissolved or suspended in saline to facilitate their administration. The isotonic nature of saline helps to ensure that the delivery medium does not induce osmotic shock to the tissues, making it an ideal solvent for intravenous drugs. The engineering of these drug delivery systems involves a multidisciplinary approach, combining pharmacology, materials science, and mechanical engineering to create devices that can accurately dispense medication while maintaining the stability and effectiveness of the saline drug mixture. In surgical settings, saline solutions are used to irrigate wounds and surgical sites, helping to clear debris and reduce the risk of infection. The engineering of saline irrigation systems requires a thorough understanding of fluid dynamics to ensure that the solution is delivered at the right pressure and flow rate to be effective without causing tissue damage. Surgeons rely on saline to maintain a clear field of vision during operations and to keep tissues hydrated, which is critical for preventing cellular desiccation and ensuring proper healing. The environmental impact of saline production and disposal is an area of growing concern, necessitating the application of environmental engineering principles. Large-scale saline production, particularly from seawater desalination, requires significant energy inputs and generates brine waste that must be managed responsibly. Engineers are developing more efficient desalination technologies, such as reverse osmosis and electrodialysis, to reduce energy consumption and environmental impact. Additionally, innovative methods for brine disposal and recycling are being explored to mitigate the ecological footprint of saline production. By applying principles of sustainability and resource management, engineers are working to ensure that the benefits of saline solutions can be realized without compromising environmental health. The journey of saline begins with the dissolution of sodium chloride in water. When sodium chloride, NaCl, is introduced into water, it undergoes a process known as solvation. Here, the polar nature of water molecules plays a crucial role. Water, being a polar solvent, has a partial negative charge near the oxygen atom and a partial positive charge near the hydrogen atoms. When NaCl dissolves, the positive sodium ions, Na+, are attracted to the partially negative oxygen atoms of the water molecules, while the negative chloride ions, Cl, are attracted to the partially positive hydrogen atoms. This interaction causes the NaCl crystal lattice to break apart as the water molecules surround and stabilize the individual ions, a process known as hydration. The dissociation of NaCl into Na+ and Cl ions is an excellent example of how the polarity of water facilitates the dissolution of ionic compounds. The dissolution of NaCl in water is governed by the principles of thermodynamics. The process is exothermic, meaning it releases energy in the form of heat. This release of energy occurs because the energy required to break the ionic bonds in the solid NaCl is less than the energy released when new interactions between the ions and water molecules are formed. The exothermic nature of this reaction is a demonstration of the system moving towards a state of lower energy, which is a fundamental aspect of the first law of thermodynamics, energy conservation. Additionally, the dissolution increases the entropy of the system, aligning with the second law of thermodynamics, which states that the total entropy of an isolated system can never decrease over time. The increase in entropy, or disorder, occurs because the structured, crystalline arrangement of NaCl is transformed into a more disordered state where the ions are freely moving in solution. The kinetics of the dissolution process also merit consideration. The rate at which NaCl dissolves in water is influenced by several factors, including temperature, agitation, and the surface area of the salt crystals. Higher temperatures provide the water molecules with more kinetic energy, increasing the frequency and force of collisions between water molecules and NaCl, thereby speeding up the dissolution. Agitation, such as stirring, helps distribute the ions throughout the solution more quickly, preventing saturation at the site of dissolution and maintaining a concentration gradient that drives further dissolution. The surface area of the salt crystals also plays a significant role. Smaller crystals or powdered salt dissolve faster due to the greater surface area available for interaction with water molecules. From an engineering perspective, the controlled dissolution of salts like NaCl is critical in various industrial processes. In chemical engineering, understanding the solubility and dissolution rates of different salts is essential for designing efficient mixing and reaction systems. For instance, in the pharmaceutical industry, precise control over the dissolution of active ingredients can affect the efficacy and delivery rate of medications. Engineers must also consider the thermodynamic properties of solutions to optimize processes such as crystallization, evaporation, and distillation. These processes often rely on the principles of phase equilibria, where the balance between different phases, solid, liquid, gas, is manipulated to achieve desired outcomes, such as the purification of salts or the concentration of solutions. Moreover, the principles of dissolution and solubility are applied in environmental engineering to address issues related to water quality and desalination. Desalination technologies, such as reverse osmosis and electrodialysis, exploit the differences in solubility and ionic mobility to separate salts from seawater, providing fresh drinking water in arid regions. These processes require a deep understanding of the interactions between ions and water molecules, as well as the energy requirements and efficiency of different separation techniques. Engineers must balance the thermodynamic and kinetic aspects of dissolution to design systems that are both effective and energy efficient. The dissolution of sodium chloride in water is a complex interplay of chemical, physical, and thermodynamic principles. The process exemplifies the importance of solvation, where polar water molecules disrupt the ionic lattice of NaCl, leading to an increase in entropy and the release of energy. Understanding these principles is not only fundamental to the field of chemistry but also critical to various engineering applications, from industrial processes and pharmaceutical formulations to environmental solutions and desalination technologies. This multifaceted understanding underscores the importance of interdisciplinary knowledge in addressing the challenges and opportunities presented by such a ubiquitous and essential process. In this dissolution process, we see the fundamental principles of chemistry at work. The strong electrostatic forces that hold the sodium and chloride ions together in the solid state overcome by the hydration forces exerted by the water molecules. This transition from a solid to a dissolved state illustrates the balance of energy and entropy, central concepts in thermodynamics. When solid NaCl is introduced into water, the polar water molecules surround the positive sodium ions and the negative chloride ions. The water molecules, with their partially charged hydrogen and oxygen atoms, interact with the ions and stabilize them in solution. This interaction effectively breaks the ionic bonds in the solid lattice, releasing the ions into the solution. This process is exothermic, meaning it releases energy, and it increases the system's overall entropy. reflecting the natural tendency toward disorder and energy dispersion. From an engineering perspective, the dissolution of NaCl can be optimized through temperature control and mixing. Increasing the temperature of the water enhances the kinetic energy of the molecules, thereby increasing the rate at which the water molecules interact with and stabilize the ions. This principle is utilized in various industrial processes where the dissolution rate needs to be maximized. Additionally, the use of mechanical mixers ensures that the solute and solvent are evenly distributed, preventing localized saturation and promoting uniform dissolution. The design of these mixers is based on fluid dynamics principles, ensuring that the flow patterns promote efficient mixing and solvation. The dissolution of sodium chloride is also a vivid example of the interplay between enthalpy and entropy in chemical processes. The enthalpy change, or the heat exchange involved in dissolving NaCl, is balanced by the increase in entropy, which drives the process forward. In this context, the Gibbs free energy equation, which combines enthalpy and entropy, helps predict the spontaneity of the dissolution process. Engineers and chemists use this equation to understand and manipulate various conditions to achieve desired dissolution rates and concentrations. For instance, in the pharmaceutical industry, the dissolution rates of drugs in saline solutions must be precisely controlled to ensure proper dosage and efficacy. Moreover, the molecular interactions during the dissolution process can be studied using advanced techniques such as spectroscopy and molecular dynamics simulations. These methods provide detailed insights into the solvation process at the atomic level, allowing scientists and engineers to design better solvents and optimize dissolution processes for various applications. In water treatment plants, for example, understanding the dissolution and solvation dynamics of different salts can lead to more efficient desalination and purification techniques, ensuring the provision of clean drinking water. In the broader scope of physical chemistry, the dissolution of NaCl in water serves as a model for understanding solubility and solution behavior. The principles derived from studying such simple systems can be applied to more complex solutions encountered in both natural and industrial processes. For instance, the solubility principles can help in designing processes for extracting valuable minerals from ores or for creating stable emulsions in food and cosmetic industries. The engineering challenges involved in scaling these processes from laboratory to industrial scales require a deep understanding of the underlying physical chemistry, combined with practical considerations of materials science and process engineering. In the context of environmental engineering, the dissolution process of salts like NaCl is crucial for managing saline waste streams and for developing effective desalination technologies. Reverse osmosis and other membrane technologies, which are central to desalination, rely on the principles of solute-solvent interactions and the ability to manipulate these interactions to separate salts from water. Engineers design these systems to optimize energy consumption and maximize efficiency, often drawing on thermodynamic principles to achieve sustainable and cost-effective solutions. The development of advanced materials, such as nanoporous membranes, is guided by a thorough understanding of the dissolution and transport properties of salts, reflecting the deep interconnection between chemistry, physics, and engineering in addressing real-world challenges. The dissolution of sodium chloride in water is a fundamental chemical process that exemplifies the principles of thermodynamics, fluid dynamics, and molecular interactions. The balance of enthalpy and entropy, the role of temperature and mixing, and the detailed molecular dynamics all contribute to our understanding and control of this process. The insights gained from studying such basic interactions are applied across a wide range of industries, from pharmaceuticals and food production to environmental engineering and water treatment, highlighting the profound impact of these principles on our daily lives and technological advancements. In industrial settings, the production of saline involves precise control over temperature, pressure, and concentration, Large-scale production often utilizes evaporation techniques where seawater is subjected to controlled heating. This process leads to the evaporation of water and the crystallization of salts. Engineers meticulously design evaporators and crystallizers to optimize energy consumption and maximize yield, adhering to principles of thermodynamics and fluid dynamics. To delve deeper into the thermodynamics of saline production, it's crucial to understand the phase changes involved in the evaporation process. The transition of water from a liquid to vapor requires a substantial input of energy, specifically the latent heat of vaporization. Engineers must carefully manage this energy input to ensure efficiency. This often involves using multi-effect evaporators, where the vapor generated from one stage is used to heat the next stage, thus conserving energy. The principles of heat transfer and energy balance are meticulously applied to ensure that the maximum amount of water is evaporated with minimal energy consumption. Additionally, the process must be conducted at precise temperatures to prevent the decomposition of salts and other unwanted chemical reactions. Fluid dynamics plays a significant role in the design and operation of the equipment used in saline production. The flow of seawater through evaporators and crystallizers must be carefully controlled to ensure uniform heating and efficient evaporation. Engineers utilize computational fluid dynamics (CFD) models to simulate the flow patterns and optimize the design of the equipment. These models help in predicting the behavior of fluids under various conditions, allowing for the design of systems that minimize energy losses due to turbulence and friction. The application of Bernoulli's principle and the Navier-Stokes equations helps engineers to design systems where fluid flow is smooth and predictable, ensuring consistent production rates. The concentration of the saline solution is another critical parameter that requires precise control. As the water evaporates, the concentration of salts in the remaining solution increases. Engineers must monitor and adjust the process continuously to maintain the desired concentration levels. This involves the use of sensors and automated control systems that can make real-time adjustments to the process parameters. The principles of chemical kinetics and equilibrium are applied to ensure that the crystallization of salts occurs under optimal conditions, avoiding the formation of unwanted byproducts. The use of advanced materials for sensors and control systems ensures that they can withstand the harsh conditions of a production environment. The crystallization process itself is a complex phenomenon that requires a deep understanding of nucleation and crystal growth kinetics. Engineers design crystallizers to provide the ideal conditions for the formation and growth of salt crystals. This often involves controlling the supersaturation of the solution, which is the driving force for crystallization. The design of crystallizers also incorporates principles of mass transfer, as the rate at which salt ions migrate to the growing crystals affects the size and quality of the final product. The application of advanced mathematical models helps in predicting and controlling these processes, ensuring that the crystals formed are of uniform size and purity. In addition to the physical and chemical principles, the economic and environmental aspects of saline production are also critical. Engineers must design processes that are not only efficient but also cost-effective and environmentally sustainable. This involves the integration of renewable energy sources, such as solar or wind power, to reduce the carbon footprint of the production process. The use of advanced materials and technologies to recover and recycle waste heat further enhances the sustainability of the process. Engineers also work on developing methods to minimize the environmental impact of the brine, a byproduct of saline production, through innovative treatment and disposal techniques. The industrial production of saline is a complex process that requires a deep understanding of thermodynamics, fluid dynamics, and chemical engineering principles. Engineers must meticulously design and optimize every aspect of the process to ensure efficiency, cost-effectiveness, and environmental sustainability. The integration of advanced technologies and materials, coupled with a rigorous application of scientific principles, ensures that the production of saline can meet the growing demands of various industries while minimizing its environmental impact. The flow of saline solutions through pipes and systems is another area where engineering expertise is crucial. Fluid dynamics principles, particularly the Navier-Stokes equations, describe the motion of saline as it flows through conduits. These equations, which are derived from Newton's second law of motion, account for the viscosity of the fluid, the velocity of the flow, and the forces acting on the fluid. Engineers use these equations to predict and control the behavior of saline as it moves through various systems, ensuring that the delivery is both efficient and effective. Understanding these principles allows engineers to design efficient delivery systems in both medical and industrial applications, minimizing resistance and preventing turbulence that could lead to inefficiencies or damage. In medical applications, for example, the delivery of saline through intravenous lines requires precise control of flow rates to match the patient's needs. The inner diameter of the tubing, the length of the tubing, and the viscosity of the saline all influence the flow rate. Engineers must consider these factors to design systems that deliver the correct amount of saline without causing discomfort or complications for the patient. In industrial applications, such as desalination plants or chemical manufacturing facilities, the flow of saline solutions through pipes must be carefully controlled to prevent scaling, corrosion, and blockages. The Reynolds number, a dimensionless quantity that predicts flow patterns in different fluid flow situations, helps engineers determine whether the flow will be laminar or turbulent. Laminar flow, characterized by smooth, parallel layers of fluid, is often preferred because it reduces friction and energy loss. However, achieving laminar flow requires precise control of flow rates and pipe dimensions, which are determined through meticulous engineering calculations and simulations. The design of these systems must also account for factors such as pressure, temperature, and the physical properties of the saline solution. For instance, the temperature of the saline can affect its viscosity and density, which in turn influences the flow rate and pressure drop across the system. Engineers use computational fluid dynamics, CFD, software to model these variables and optimize the design of pipes and pumps. CFD simulations can predict how changes in temperature, pressure, or flow rate will affect the overall system, allowing engineers to make informed decisions and avoid potential issues before they arise. Furthermore, the materials used in constructing the piping systems must be carefully selected to withstand the chemical properties of saline solutions. Stainless steel, PVC, and other corrosion-resistant materials are commonly used to prevent degradation and ensure the longevity of the system. The choice of materials also affects the thermal conductivity of the pipes, which can influence the temperature of the saline as it flows through the system. Engineers must balance these considerations to design systems that are both durable and efficient. In addition to the physical design of the piping systems, engineers must also consider the control mechanisms used to regulate the flow of saline. Automated control systems, which use sensors and feedback loops, can adjust flow rates and pressures in real time to maintain optimal conditions. These systems rely on advanced algorithms and control theories to respond to changes in the system, such as variations in demand or fluctuations in pressure. By integrating these control mechanisms with the physical design of the piping systems, engineers can create highly efficient and reliable saline delivery systems. The flow of saline solutions through pipes and systems involves a complex interplay of engineering and physics principles, from the Navier-Stokes equations that describe fluid motion to the materials science that ensures system durability. Each aspect of the design process requires careful consideration and expertise. By understanding and applying these principles, engineers can develop efficient, reliable systems that meet the demands of both medical and industrial applications, ensuring that saline solutions are delivered precisely and effectively where they are needed most. In the realm of medicine, Saline solutions play a pivotal role that extends well beyond mere hydration. At the forefront of medical applications, saline is indispensable for maintaining the delicate balance of electrolytes crucial for normal bodily functions. This electrolyte balance is meticulously regulated by biomedical engineers who design and develop sophisticated infusion systems. These systems, equipped with precision sensors and advanced feedback mechanisms, ensure that saline is administered to patients at precisely controlled rates. The engineering behind these infusion systems is complex and multifaceted. Engineers must consider factors such as flow dynamics within the delivery mechanisms, ensuring that the saline solution flows smoothly and consistently to the patient. Fluid dynamics principles, including the Navier-Stokes equations, are applied to optimize the design of pumps and tubing, minimizing resistance and turbulence. This not only enhances the accuracy of delivery but also reduces the risk of mechanical complications that could compromise patient safety. Moreover, the infusion pumps themselves are marvels of modern engineering. They incorporate microprocessor-controlled algorithms that calculate and regulate infusion rates with high precision. These algorithms rely on real-time feedback from sensors that monitor parameters such as pressure, flow rate, and volume. By continuously adjusting the delivery parameters based on this feedback, engineers ensure that the patient receives the exact amount of saline required to maintain physiological homeostasis. The materials used in these infusion systems are carefully selected to ensure compatibility with saline and biocompatibility with the human body. Engineers choose materials that resist corrosion and degradation when in contact with saline, thereby maintaining the integrity of the system over time. Polymer science and material engineering play critical roles in developing components that are not only durable but also safe for prolonged medical use. In intensive care units and surgical settings, where precise fluid management is crucial, saline infusion systems provide healthcare professionals with the tools needed to deliver tailored treatment regimens. Whether administering medications, replacing lost fluids, or managing electrolyte imbalances, the ability to control saline delivery accurately can significantly impact patient outcomes. Biomedical engineers collaborate closely with healthcare providers to ensure that these systems meet clinical needs while adhering to stringent safety and performance standards. Looking ahead, the field of biomedical engineering continues to innovate, driven by advances in sensor technology, automation, and data analytics. Future developments may include smart infusion systems capable of adaptive responses based on real-time physiological data from patients. These systems could revolutionize patient care by further enhancing the precision and efficiency of saline delivery, ultimately improving therapeutic outcomes and reducing healthcare costs.